Hello and welcome to section 4.9, which if you watched the last video, which was actually 4.7, we skipped 4.8. In section 4.9, we really get into an introduction of what chapter 5 is going to cover. So on exam 3, I'm not going to include this section because it really sort of deviates a little bit from the rest of chapter 4. And really all of chapter 5, which will be exam 4, covers anti-differentiation as a whole. So this is a nice introduction to chapter 5, but nothing you need to rush to get through in order to complete exam 3, which is coming up. So when we looked at a function and we talked about differentiating that function, that process is sort of feels for us right now like a one-way street. The question is, can we go backwards? If I handed you the derivative of some function, could you recover that original function? So if given the function, you know how to find the derivative, but what about the other way? If I gave you the derivative, could you find some original function f of x that came from, or where that f prime of x came from? And the answer is, of course, well, yeah, we can do that just by kind of reversing the process. And that's where we talk about what are called antiderivatives. And this is, again, like I said, what all of chapter 5 is really going to hone in on, the process of going the other direction with it. So a function, and we're going to use capital F of x, is called an antiderivative, rather than squeeze that in over on that side over there. There we go. So a function which will denote capital F of x is called an antiderivative of f of x on an interval, we'll just call it interval I, if f prime, and by that I mean the capital F prime of x, is equal to f of x for all x in that interval. Which we just call I. So there is this function that we have when we find its antiderivative. We just need to label it something different. We call it capital F of x. If I differentiate that capital F of x to get capital F prime of x, I should get back to my original function, f of x. All right, so say we have some function out there. We'll say f of x is equal to, let's do 3x squared. That means that somewhere out there must be a function, capital F, such that when I differentiate it, I get f of x. I get 3x squared when I differentiate it. The question for us right now is, what is that function? Is there some function out there, capital F of x, such that when I differentiate it, I get f prime, or capital F prime, which is our function that we're talking about. So this is a derivative. I know it doesn't have the f prime notation, but in terms of capital F of x, it looks like a derivative. But the derivative can always just be relabeled as a function itself. Right? The derivative of a function is a function itself. So what we're doing is we're looking out there and saying there's got to be some function that when I differentiate it, I get 3x squared, which is this function that I'm looking at. Well, the answer is, yeah, sure, but we do have some options. If I were to differentiate x cubed, I would get capital F prime of x to be 3x squared. And you think, oh boy, that was easy. Right? Instead of going down a power, I go up a power. But there's some more functions out there that I can choose, like x cubed plus 1. If I differentiate this function, I still get f prime, capital F prime, to be 3x squared because the derivative of a constant is 0. Okay, now which one is it? And how do I know which one it is? Or how do I know it's not my original function f of x that was out there that I differentiated? Maybe it was x cubed minus 100. The derivative of negative 100 is still 0. I still get my function. And this can go on and on and on forever, right? No matter what that constant is. Here it was really just plus 0, right? So when we differentiate something and we have all these rules, we know exactly what function we're going to get. If I chose any of these for capital F, I would get my derivative of capital F to be 3x squared, which is what we're calling this new function that we found. But if we start with this new function and try to recover the original function that it might have came from, my list is endless. My choices are endless. And it's all because of this extra little constant. When we differentiate, we know we're getting rid of that information. But when we anti-differentiate, we have to try to recover that information. Without any source or any knowledge of what that constant was, then we have to be a lot more general in terms of how we write out these functions. I can't declare that it's exactly this one and not any of the other ones on the infinite list that I have. So again, we start with a function and differentiate it, which is also a function. Now we're calling that the original function we start with and saying anti-differentiate that to get back to that antiderivative. And you can see that that process leaves a little bit of vagueness behind. So we're going to just have to learn how to handle that constant. Right, so this is our introduction leading into chapter 5. And we'll just basically piggyback off this theorem for the rest of the section. If f, capital F of x, is an antiderivative of f of x, then the most general form of f of x is capital F of x plus c, where c is a constant. So what that tells us is when looking for the antiderivative of some function, I really just have to add on this extra plus c, because without enough information to recover that actual constant, I still want to leave a placeholder there. C could be 0, but I don't know that for sure. C could also be 50. Right? I don't know that for sure. C could be negative 20. C could be plus pi. C could be minus pi. So I don't know what that constant is, so I have to be very careful. So again, say we have some function, right, f of x is 3x squared plus 2x plus 1. Can I find that antiderivative capital F of x? So if I want to find the antiderivative, I would have to figure out what function would give me 3x squared when I differentiate it. Well, x cubed, when I differentiate it, the 3 comes down because of power rule. I reduce 1 from the power. So this is a perfect candidate for getting this when I differentiate. X squared is a perfect derivative, or sorry, the perfect antiderivative of just 2x. X would be a perfect candidate such that when I differentiate it, I just get 1. But who knows what this constant was? That plus c is a perfect candidate for if I differentiate a constant, I get 0. Right? But I don't know that this antiderivative is going to stop here. There could be a constant. So what's happening is you're taking this what we used to call f of x, and you're differentiating this function to get f prime. And that's what we used to do. We used to start off and say, okay, this is f of x, this is f prime of x. Now we're ignoring the fact that we're starting with this function and differentiating. We're starting with this function and finding the antiderivative going up. And that's why they use this capital F notation. But essentially that's what you're doing. You're starting with a derivative and recovering an original function from that derivative versus starting with the function and getting the derivative out of it. So you can see we've got a forward process and a backward process. I could start with this and differentiate to get this, or I can start with this and anti-differentiate to get this, the blue. So we're going to have to just, for now, trust that plus c gets tacked on there, and we don't have enough information quite yet to find it, but I'll show you. If they give you enough information, you can recover that constant that actually works and gives you the exact antiderivative that you need. So here's just another quick example. Say we're starting out with y prime is cosine of x. Can I find the original function y? That is to say, when I go in this direction, can I get the antiderivative? So going from here to here, I want to find the antiderivative. Oops, let me try to spell that right. Antiderivative. That when I differentiate it, I would get y prime. Well, if I differentiate the sine of x function, I would get cosine of x. So this is a great candidate, but it's not the most general candidate because I could have had sine x plus 7. I could have had sine x minus 30, sine x plus 50 billion, right? That 50 billion, when I differentiate it, I'd still get this function. So I need some sort of general function that fits the pattern of this is what I start with y. When I differentiate, I get y prime equals cosine of x. No matter what that constant is, when I differentiate it, it's 0. So this is the most general form of the antiderivative, right? And I should be able to do this all day long. If I take this and differentiate it, boom, I get y prime. If I take y prime and find the antiderivative, I get back y prime, y prime, right? Differentiate, anti-differentiate, differentiate, anti-differentiate. All you're doing is taking, one step forward, one step back, one step forward, one step back, one step forward, one step back. If I were to differentiate this function twice, I should be able to find an antiderivative for that function and then another antiderivative for that function and get back to this function. Right? But you'll see as you differentiate, when you differentiate, you start losing information, like the constant starts to disappear. So when you go to anti-differentiate, you just got to pick up that general information again, unable to recover the exact information because it's been lost. So let's take a function and see if we can. Now, I know it says find all functions, but that's just because we want the general form, which will cover all the functions. Find all functions g such that g prime of x is equal to 1 over 1 plus x squared minus 7x cubed plus 6 e to the 2x. So again, in chapter 5, we get a lot more, I guess you'd say, like rules or strategies for finding antiderivatives because they can be tricky. Like for differentiating, we got product rule, quotient rule, chain rule, all this great stuff. So in Chapter 5, we'll pick up a lot more rules. But for now, we just kind of have to massage our brains to start thinking in the backwards direction. What function out there? We want to find all functions g of x such that their derivative looks exactly like this. Well, g of x, we still do have this like term by term by term situation where if I differentiate something, I should get 1 over 1 plus x squared. Aha, there is a function out there that we know of such that when you differentiate it, you get 1 over x squared, and that is the arctangent function. When you differentiate arctangent of x, you get 1 over 1 plus x squared. Therefore, the antiderivative of 1 over 1 plus x squared must be that arctangent of x function. If I differentiate and then anti-differentiate, those two go back and forth. So that is the nice function to take care of that. Again, next term, I'm looking for a function such that when I differentiate it, I get negative 7x cubed. Well, this must be some 7x to the 4th power, but be careful because when I differentiate this, I get 4 times 7x cubed, and that's 28x cubed with the minus sitting out front, and that's too much. So I need to, rather than multiply by that new power, I need to account for division of that power so that when that 4 comes down as a multiple and I differentiate, the 4 and the division by 4 cancel each other out, and I get 7x to the 3rd power when I reduce that power thanks to power rule. So we do have to be careful. And again, right now we're just kind of massaging our brains so that we write something down and then we'll differentiate that thing to make sure that we're getting what we actually want. Similar situation here, plus 6e to the 2x. Well, when I differentiate 6e to the 2x, I get 6e to the 2x, but then chain rule kicks in and tells me I have to multiply by 2, which would give me 12e to the 2x. So this is too much. I need to divide this by that 2, because when I differentiate this, 6e to the 2x, I'm going to get 6e to the 2x times 2. That extra division by 2 will help cancel out. So that means to cover all functions, I also need to squeak in a plus c. Why? Because when I differentiate this constant, it's gone. So now I've got arctangent or tangent inverse of x. We'll have to leave this 7/4 x to the 4th power. I can clean this up as 3e to the 2x, and then the plus c. So again, the way to check to make sure that you've got all functions g that satisfy this, differentiate arctangent, there it is. Differentiate this, the 4 comes down, cancels out, I get 7x cubed with the minus, good. Differentiate this, I'll get 3e to the 2x, but then chain rule says I multiply by 2, 3 times 2 is 6, check. And if I don't have this plus c here, then I only have one specific function g, and I don't have the function g of x that has a plus 1 here, and a plus 2 here, and a plus a half here, and a plus pi here. And then there's an infinite list of functions, and each one of those functions on that list has a different constant added on. But no matter how infinite that list, if I pick any g of x function that has these 3 terms and then any constant, and I mean any, it could be decimals, it could be fractions, it could be irrational numbers, it could be square root of 3, like whatever you want. There's an infinite list, and each one on that list has a different constant. But all of those g of x functions on that list, those constants disappear anyway, and I always get back this function. So when they say find all functions, it's not like you're finding 30 functions or 50 functions or 10 functions. You're finding an infinite list of them. And this plus c is what's giving you that most general form and creating that list for you. And that kind of leads us into the question of, well, can I find a more specific function? Can I find the one and only function that refers to this specific derivative? You can, but you need a little more information initially. They need to tell you a little bit more about this function that you're going to recover. you need to be able to solve for c based on some extra information that they give you. Otherwise, you just have to leave it with the plus c to get the general antiderivative. But if you're lucky and you get some more information, then you get to solve it a little bit further. So here is find f of x. If f prime of x is 5x to the fourth minus 3x squared plus 4, and we know that f of negative 1 has to equal 2. So say they've given us this little extra bit of information that we get to use. Well, here's my derivative. My goal is to recover my original function f from this derivative. So I need to find a function out there that would give me 5x to the fourth when I differentiate it. Anti-differentiating that, I get x to the fifth, right? Because differentiating x to the fifth gives me 5x to the fourth. Anti-differentiating 5x to the fourth must get me back to x to the fifth. Similar here, minus x cubed, because if I differentiate this, the 3 comes down and I reduce the power to get minus 3x squared. So differentiating x cubed gives me this, therefore anti-differentiating this gets me back to minus x cubed. Over here we've got plus 4x, because again, differentiating 4x gives me 4, thus anti-differentiating this constant 4 gets me back to 4x. But I still need my plus c, because differentiating any constant you can think of gives you this plus 0. So finding the antiderivative of 0 gives me back a constant. It returns a constant back to my original function. Now don't get me wrong, that constant could also be 0, but that is just one possibility out of an infinite number of possible constants that could be added on. So just because it's one possibility doesn't mean I want to get rid of it. But now I have the information that says f of negative 1 must equal 2. So I have my general form of my function f, but now I also get to use this piece of information that says if you plug in negative 1 into this function f, it will equal 2. So what it does is it allows me to plug in a value for x and set that function equal to whatever that output is. So I know that negative 1 raised to the fifth power, which is negative 1, minus negative 1 cubed, which is minus negative 1, which is plus 1, plus 4 times negative 1, that's minus 4, plus some constant should all equal 2. And now I can just solve for that constant. Well, minus 1 plus 1, that's pretty easy. They take care of each other right off the bat. And I can add 4 to both sides to say that c must equal 6. So given that extra information, you can now use that extra information to find f of x. F of x must be x to the fifth minus x cubed plus 4x plus 6. All right, so using that extra information that they gave you for the constant, you plug that constant now in because you're confident that you know that the constant has to be this value. Otherwise, this would not hold true. The only way this holds true is if you get the most general antiderivative, plug this x value in and set it equal to this y output. And if that's the case, then that has to be that constant. Now there's no more vagueness of, okay, this is just a general form of an antiderivative for this derivative, but this specific derivative with this specific property must have this specific antiderivative. So again, when differentiating, we don't need extra information to get the correct derivative, but when anti-differentiating, we need that extra information to get that specific antiderivative. And then just one more quick example, because again, this is just sort of an introduction to Chapter 5. So, we've looked at before a couple problems that talked about things like position, velocity, and acceleration. So just to get one that's a little reminiscent of that type of stuff, I guess you can't even really call this a word problem. It's too short to be called a word problem. But a particle is moving with the given data and our goal is to find the position function. So they start by telling us that the velocity v of t is given to be t squared minus 3 square root of t. And they tell us that s of 4 is equal to 8. Remember, for these position, velocity, acceleration, right, we talk about s of t, the derivative of the position gives us the velocity, the derivative of velocity gives us acceleration. So we're starting with the velocity, and rather than differentiating, we now have to anti-differentiate to get back to the position function. And then they give us some information about the position function so that we may recover the exact antiderivative, not just some class of antiderivative that has this general plus c that we can't figure out. They give us that extra piece of information to figure out what that plus c is. So we'll take this function and we will recover the position function. So right off the bat, notice that v of t has this square root in it. So I'm going to write that as a 1/2 power. So I'm not finding the antiderivative. I'm just simply rewriting the radical as a 1/2 power. So we can see that power a little easier. And then I smudged it. Okay, now let's recover that position function, the most general form with the plus c in it. So I need to go up a power, but I better divide by that 3, because if I differentiate t cubed by itself, I get 3t squared. This is not 3t squared. But if I have this division by 3 in my position function, then when I differentiate my position function to get velocity, this power of 3 will come down. 3 divided by 3 is 1, and I'll reduce that power to get t squared, and I'll just get t squared, which is what I have to have. So I need that little extra division to help me out. Minus. Now again, there is a multiple of 3 here. I have t to the 1/2, but I have to go up a power to the 3/2. Meaning now that I have t to the 3/2, if I differentiate this, 3/2 minus 1 is 1/2, so I'm good on the power. But this 3/2 is going to have to come down as a multiple, and I'll get 3/2 times 3, which is 9/2. This is definitely not 9/2. So I want that 3/2 to cancel out, so I'm going to divide by 3/2, so that when that power 3/2 comes down, I multiply by 3/2, I divide by 3/2, cancel, cancel. We'll clean that up in a second. And then, of course, the plus c has to come into play because there's something that might have gotten differentiated down to 0. I want to be able to recover that something correctly based on the information given. So I'm going to write s of t is 1/3 t cubed. Yes, that gives me t squared, which is great. Minus, rather than leave it sloppy like this, dividing by 3/2, I'm multiplying by 2/3. So I can clean it up like this. Yeah, differentiating this, the 3/2 comes down as a multiple. Multiplying by 2, dividing by 2, leaves that multiple of 3, and I'll get t to the 1/2 power. So I can differentiate this to check to make sure that I'm getting the correct antiderivative. This is just my plus c. So I just rewrote that weird stuff with the complex fraction there. Now we know that s of 4 is equal to 8. So I'm going to plug in 4. And I know that when I plug 4 into this most general form, it has to be equal to 8. So wherever I see t, I plug in 4. And now I can just simplify. This is 1/3 times 4 cubed is 64 minus 2 times, this is the square root of 4 cubed. Well, the square root of 4 is 2. Cubing 2, I get 8. But there's also this multiple in front of it. Plus c is equal to 8. So I've got 64/3 minus 16 plus c is equal to 8. So I come up here for a little more room. I'll just underline that, I guess. That'll be the best way to do that. So what I can do is get a common denominator. Here's 64/3 minus, if I do 16 times 3 and divided by 3, let's see, 16 times 3 will be 48. So this will give me 64/3 minus 48/3 is 16/3. Let's go ahead and subtract 16/3 on both sides. So I can get my constant c. 8 times 3 is 24. So I'm just getting a common denominator, 24 minus 16 over 3. That'll give me c is 8/3. So I'm going to take that information and bring back my position function. Thus, s of t must equal, now much more specifically without the general plus c, s of t, I don't want the general form, I want the very specific function, 1/3 t cubed minus 2t to the 3/2, or you could return it back to that radical bar notation if you like. But I'm not going to write plus c anymore because I have very specifically found what my constant is. It must be 8/3. All right, so now you have a actual position function that you can differentiate to get that velocity function, and it meets that criteria that when t is 4, you actually have 8. And you can check that by plugging 4 into here. I don't have my calculator on me, so I'm not going to sit there and do it. But you can check that. So again, you can see how, basically the whole course we've been differentiating, going one way. Now we just kind of have to tweak our brain to start thinking backwards. How can I recover that original function? And again, we'll get tons of rules in Chapter 5. 4.9 is more just of an introduction as to what the rest of the course is going to be. So all the rest of the course, we're going to be doing a lot of just antiderivative stuff. We still might need to take a derivative here or there, but mostly it's going to be antiderivative stuff. So again, as far as Exam 3 goes, 4.1 to 4.7, and I believe we skipped 4.6 as well. This is all going to be Exam 4 stuff, so I'm not even going to put it on this exam. We'll hold off till we get the proper rules and stuff in Chapter 5. I think that's just be a little bit better for Exam 3 to make it all about differentiating rather than mixing this in the bag. So thank you very much, and I'll see you back in the new section, Chapter 5.